Good morning to one and all. My name is Sohit from ECED section, roll number J8. Today, my topic is about an open source EDA flow for asynchronous logic. Introduction. Scalable computer systems are designed as a collection of modular components that communicate through well-defined interfaces. The interfaces must be robust to delays and uncertainty in the physical implementation of communication. This view applies to computer systems at many levels at abstraction. The internet is a collection of communicating computers with message passing through the internet protocol. A modern data center is a collection of servers that communicates via message passing over commodity network hardware. Even large software systems consist of a collection of modules that uses well-defined application programming interfaces, that is APIs, to communicate. Almost all computer systems disciplines have made the wise choice to partition their problem into components that communicate via protocols that are independent of their physical realization, such as timing, energy, or size. However, in current chip designs, this modular approach is abandoned in favor of global synchrony. A global synchronization signal, the clock, dictates the time budget for every step of the computation, regardless of what is being computed. The clock design. Although this clock design paradigm dominates the design of computers today, engineers are struggling to preserve the fiction of simultaneity required by the clock even within an individual chip. This struggle is an inevitable result of advancing technology. As transistors get smaller and faster, the delay of communication over wires dominates the cost of local computation with transistors. Such progress renders the clocked paradigm a poorer and poorer abstraction for chip design. Modern application-specific integrated chips (ASICs) are designed as a collection of small clocked islands that communicate via interfaces that break the clock abstraction. Development of EDA flow. To address the challenge, we are creating a collection of open source electronic design automation, that is EDA tools that isolate the designer from the details of the physical implementation technology, especially when it comes to delays and timing uncertainty. The approach is based on an asynchronous, modular, and herential design methodology for complex chips, and it permits component reuse from one technology to another with little or no modification. While individual modules of the chip can be clocked, the overall system uses an asynchronous integration approach to achieve modular composition. Hence, the EDA flow being developed supports a combination of timing styles in an integrated framework. Asynchronous logic, a unified flow. There are a large number of different asynchronous logic families. Historically, each of these families were developed by different research groups with differing terminology and design methodologies. Instead, over the years, mainstream industrial strength ASIC flow that is provided by the major EDA vendors converged on a core synchronous EDA flow that supported a limited set of options. Today, those options include flip-flop and some latch-based designs with excellent support for single clock designs. and limited support for heterochronous designs. Asynchronous logic for EDF flow. The convergence that occurred in the synchronous domain did not occur in the asynchronous logic domain, and hence the EDA landscape for asynchronous logic is quite bleak in comparison. Example flows developed for asynchronous design include Haste and Balsa, and more recently Protis. Each of these flows supports the restricted style of asynchronous design and uses commercial synchronous tools for physical design automation. Since the asynchronous and synchronous physical design tools do not have a correct view of timing for asynchronous logic, conservative workarounds are used to constrain the design in order to ensure a wild implementation. This approach has also been adopted by many academic groups to leverage the investment made by the commercial EDA industry. The open source flow. The key steps of the design flow we have developed are design expansion or elaboration, which expands the design and customizes it based on the parameters specified by the user. Technology mapping and gate generation, which identifies the unique gates needed to implement the asynchronous circuit and generates the layout for the cells if a new gate is found in the design. Static timing analysis, which implements the asynchronous equivalent of timing analysis, determines the performance or power of the design and checks any timing constraints needed for correctness. Design partitioning and floor planning. Asynchronous timing driven placement. Timing driven global routing followed by detailed routing to complete the physical implementation. The rest of the steps are standard, including inserting fill and adding the pads and seal ring. The flow is summarized in below figure. To interoperate with commercial tools at key steps, we can import or export designs using standard formats such as a Valorant list, Spice Netlist, and LEF or DEF. We also accept parasitic for information via SPEF flies and timing information using the .lib format. All the tools, both those under development and those ready for use, will be distributed. Design flow for asynchronous logic. Design, expanded design, technology mapping. Technology mapping is divided into new cell to characterizer, and new cell is further divided into layout editor, technology mapping, floor plan, placement, routing, layout, finishing. All are divided into asynchronous starting timing engine. Thank you.